In this unit, we're going to move into talking about imines, enamines, and iminium ions, and these are really nitrogen analogs of carbonyl-based compounds and intermediates that we've seen previously. And this is a point that I'll return to again and again and again, that when you work with imines and enamines, you should really in the back of your mind be thinking about the analogous carbonyl chemistry. Imines are sort of glorified carbonyl groups, as we'll see, and enamines are really glorified enols. Changing oxygen to nitrogen does have some effects. For example, generally enamines are more nucleophilic than enols because nitrogen is less electronegative than oxygen. But generally speaking, the types of reactions they engage in are exactly analogous to reaction types we've already seen for carbonyl groups. Things like electrophilic addition to the alpha carbon of an enamine, or nucleophilic addition to the carbon of an imine in the C-N double bond. These reaction types are analogous to carbonyl reactions we've already seen, and drawing on those analogies is going to help you reason mechanistically through these reactions and predict products with high fidelity. So our learning objectives: first, we're going to recall methods we've already seen for preparing imines, enamines, and iminium ions from ketones and aldehydes using condensation type reactivity. Then we'll recognize imines and enamines as tautomers in the same way that ketones and enols are tautomers, and we'll learn how to draw the enamine tautomer of a given imine and vice versa. We'll look at a reaction that engages iminium ions as electrophiles that is analogous to the aldol reaction called the Monish reaction. And it's a great way to form not beta-hydroxy ketohides as in the aldol reaction, but beta-amino ketohides. And we'll apply that reaction in synthesis. And then we'll look at Stork-enamine reactions, which use enamines as nucleophiles rather than enols or enolates. And enamines hit this nice sweet spot between the reactivity of enols and enolates. They're not as nucleophilic as enolates, but they're more nucleophilic than enols, and this expands what we can do alpha to a carbonyl ultimately derived from an enamine, synthetically speaking. So we're going to apply those Stork-enamine reactions in synthesis as well. And then we'll recognize enamine and imine-like structures in heteroarenes and substituted benzenes. And this is actually key for understanding the reactivity and properties of heteroarenes in particular. A lot of these structures can look sort of exotic and rather cryptic, but when you recognize the enamines and imines built into these structures, for example, the nitrogenous bases of DNA are a great example of this in action, you start to more easily understand where these structures come from biochemically and how they might react, as well as their properties, their hydrogen bonding potential and other things like this. And in particular, we're going to look at pyridoxal phosphate, which is an important biochemical cofactor that forms imines. Basically, it's an aldehyde. The al suffix is sort of evidence for that. That is in the business of forming imines with lysine and other nitrogen-containing molecules in biochemical systems. And those imines can do interesting things. And we'll dig into that chemistry a little bit at the end of this unit. First, let's briefly review how we can make imines and enamines from a starting ketone or aldehyde. And the idea here is condensation in the presence of an acid catalyst of the amine nucleophile with the ketone or aldehyde. And here we have divergent outcomes for secondary amines, which contain two R groups linked to the amino nitrogen, HNR2, and primary amines, which contain one R group linked to the amino nitrogen, H2NR. In both cases, the amine first adds to the carbonyl carbon, and we get a carbonyl amine intermediate. And in this intermediate, we might have an H linked to nitrogen or a second R group, depending on whether the amine is primary or secondary, respectively. And the outcomes diverge here because whether we have an H there or not dictates whether we can eliminate to form a C-N double bond in a neutral product or not. So for example, in the case of a secondary amine, we don't have an H here. We've got two R groups linked to the nitrogen in the case of a secondary amine. So elimination has to occur from the alpha carbon with OH. A molecule of water is eliminated, and the resulting product is an enamine. And we can see the secondary amine as an NR2 group with a single C-N bond in that product. But for a primary amine, we have an H linked to the nitrogen, and that can be eliminated with OH. Loss of a water molecule occurs, and we get a product containing a C-N double bond, and that is the imine. So we can make imines or enamines depending on the substitution pattern of the amine nucleophile, and this works great with ketones and aldehydes. Now, imine and enamine groups also show up in larger structures such as heteroaromatics, and this same kind of reactivity can be used to establish those groups in these larger structures. So here are 4 examples that contain embedded imines or enamines. And what I want you to do at this point is pause the video and see if you can spot the imines or enamines in these structures. All right, here they are, highlighted in purple. And a point that I really want to make on this slide is that each of these can be made through condensation type reactivity like you see at the top of this slide. For example, pyrrole, which is this structure, can be made via the condensation of a 1,4-dicarbonyl compound, a compound with carbonyl groups here and here, with ammonia, or a related compound that's sort of a 1,4-dicarbonyl surrogate. Maybe we have, for example, an acetal here, or a diacetal, or something along those lines. Any sort of 1,4-dicarbonyl analog will condense with ammonia, essentially forming 2 enamines in one reaction, and pyrrole will be the product. And that is driven by the aromaticity of this molecule, and that's the case with a lot of these. Imidazole is the same. Formic acid, or formate, can be used in this capacity to form imidazole through an analogous sort of condensation type reactivity. So keep this in mind, not just for sort of the vanilla formation of acyclic imines and enamines, but also for the synthesis of these heterocycles and substituted benzenes. Similar reactivity can come into play. Tautomers are structures that differ in the position of a hydrogen atom along a conjugated system containing at least one heteroatom. And enols and their keto forms are the classic tautomers that we've seen previously. Imines and enamines are also tautomers of each other, particularly when the enamine contains at least one NH, so that that H linked to the nitrogen can be moved to the alpha carbon to form the imine tautomer. So let's recall, first of all, enol-keto tautomerism. Recall that the idea there was in the enol, we had an H that was linked to oxygen, the carbonyl oxygen. In the keto tautomer, that H was linked to the alpha carbon, and the double bond shifted. In the enol, we had a CC double bond. In the keto tautomer, we had a CO double bond. Something very similar is going on with NH enamines and imines. So take a look at this enamine. Notice we have an H linked to the nitrogen. If that H is deprotonated and then the alpha carbon is protonated, with formation of a CN double bond right here, we have formation of an imine. So these are tautomers, right? They differ in the position of an H about a 3-atom conjugated system, NCC, containing at least one heteroatom. In this case, it's a nitrogen. Like keto-enol tautomerism, the mechanism of interconversion of enamine and imine tautomers does not involve concerted proton transfer in a single elementary step. Instead, 2 proton transfers are involved, and this is always acid or base catalyzed, and whether deprotonation or protonation occurs first depends on whether we're using a base or acid catalyst, respectively. And one last point that's on the slide that's worth pointing out is that this enamine and imine are constitutional isomers, as are all tautomers. And so we'd expect them to have different properties, reactivity, that sort of thing. For example, the imine is electrophilic at this carbon, the carbonyl-esque carbon, right? The carbon that's analogous to the carbonyl carbon in the CO double bond, whereas the enamine is nucleophilic at the alpha carbon. As a result of its resemblance to an enol, we can think back to the nucleophilic nature of that carbon that we've seen many times to this point in the course. If we protonate an imine or enamine, the result is the conjugate acid of the imine or enamine, and this is referred to as an iminium ion. Notice that in both cases, we end up with an iminium ion. Protonating the imine involves just using the lone pair on nitrogen directly. Protonating the enamine, to retain electron delocalization in the conjugate acid, we push down from the nitrogen and actually protonate at the alpha carbon, which is actually the most basic position in an enamine. This gives the same iminium ion type of intermediate in both of these cases. And the iminium ion is a fantastic electrophile at that highlighted carbon in blue. It's a better electrophile than a neutral carbonyl, right? Not as good as a protonated carbonyl if we think through electronegativity and formal charge ideas, but it's better than a neutral carbonyl group, CO double bond. So it's a great electrophile, and we can add nucleophiles there. And starting to think about the reactivity of imines and enamines, a great example comes from biochemistry and the so-called class 1 aldolase enzymes. These use an enamine formed via condensation of this substrate with a lysine residue in the enzyme active site. This enamine right here is the nucleophilic partner in an aldol reaction. So here we have an enamine. After this condensation, that alpha carbon can act as a nucleophile. And this establishes an important carbon-carbon bond in the forward aldol reaction of this substrate right here. This link will take you to a crystal structure of the aldolase enzyme where you can see the substrate or a substrate analog inside the active site.